Let's start again. So we're happy to have for the second talk Mikhail Lifshits from St. Petersburg State University, who will talk about breaking the Brownian chain, time and place. Please.
Okay, nice to be here. Many thanks to organizers for inviting me. I will talk about joint work with Frank Aurzada and Volker Betz, both from Technical University of Darmstadt. A nice experience to talk at your seminar, a little bit strange way to make a first talk in Israel, but nevertheless, let's take this advantage. From the bird's flight, the problem belongs to the following class. We consider particle systems that have two phases. One is some deterministic force, and another is a diffusion, so that deterministic forces like attraction or repulsion are determined by the configuration of particles, and diffusion of particles has no reason. It is some intrinsic property. And we want to understand how do these two natures, so to say, coexist jointly. So we will consider just one problem belonging to this class. Of course, a natural tool for studying such systems is to write some stochastic differential equations where shifts, say, are responsible for deterministic forces and diffusion is naturally present. But I would like to say that writing an equation is not equivalent to solving the problem, because usually we want to get some specific properties of the system. So we have to know something about the solution, and this needs more steps than just writing equations. So we will explore some particular example, and on the first slide I will explain the problem. So this is an object that was studied before us by physicists and mathematicians. I will give some references below. So what is a Brownian chain? This is something rather simple. Everything happens on the real line. So you have d+1 particles with the names 0, 1, and so on up to d. And they are located at the corresponding points at the beginning, 0, 1, 2, and so on until d. And there are several things that occur. Okay, the particle 0 is fixed at 0. It doesn't move. The last particle, we pull it with some small speed epsilon, so it moves uniformly. And all the rest particles move, and also they experience Brownian motion. But there is every particle experiences independent Brownian motion, but there are also forces between the neighboring particles. Oops. Sorry. There is some attraction. There is some attraction. Particles do not like to be far away from each other. All this can be written as a system of stochastic differential equations. So here it is. We have d minus 1 independent Brownian motion. The first equation corresponds to the initial position. The second equation says that the zero particle is fixed. The blue equation says that the last particle moves uniformly. And the last equation reflects the movement of an interior particle, so that the particle is attracted both to the right and left neighbors, and the entire shift parameter then is described by this shift term. And then there is, of course, Brownian motion. So we have the system of equations. And since this part is linear in X, the resulting process will be a multivariate Gaussian process. Most of the time I will discuss Gaussian processes, but at the end of the talk, I will move to more or less arbitrary potentials and will show that the results doesn't change that much. So far I described what is the Brownian chain. Now, what is the break I'm going to study? This is the simplest way to represent the break. We think that the chain will break if a difference between two neighboring particles reaches some level B, which should be bigger than 1. But for simplicity of writing, I will just let B equal to 2 in most of the, during the most of the talk, B will be just equal to 2. So I just want to know where the breaks occurs and when does it occur. So let us define the break time tau. First, we define the break time at a position I, somewhere here. We have a particle I and I minus 1. And when the difference between the positions of two neighboring particles reaches this critical level, so we say it's a break. And then we take the minimum among the break times for all pairs that are here. There are d possible places of the break, and this tau will be the break time. And there is a trivial observation that we have a natural deterministic bound for this random variable tau, because we know the distance between the first and the last particle, so we know the average distance between the particles. And so this is the time, tau t star is the time when the average distance reaches the critical level. Of course, if the average reaches this level, then the minimal time is already achieved.
Is it clear that Ti is always finite? I mean, are they all going to break away from each other?
Yeah, it is exactly by the reason I just described, because the average distance between the first and the last particle is growing linearly. So at some point it will reach the critical level. And if the average reaches critical, then the maximal distance, of course, is bigger than average, and then hence it is.
Yes, but wait, but that's I mean, that reasoning works for tau, not for tau I, right? I mean, we could imagine that
okay, yes, sure. Yeah. Formally, you are right. Formally, you can imagine a situation when two particles stick each other and they continue moving together and never go apart. But since I'm interested in the infimum, this doesn't matter. This is first answer. And the second answer is that we prove that in our system, every pair of particles,
they all break apart. Okay.
Yeah. Okay. Now there is another thing. Break position. This is exactly the I, such that tau equals tau I. So tau the I this break position takes values 1, 2, and so on d. We have d intervals. So, and one of the nice things of this problem is that the distribution of this tau can be calculated, and it is not that it is not obvious. If you pull very strongly, then the break will occur here at the last link. But otherwise, the distribution is somewhat unexpected, and we will see it later. Okay, so let me state the problem exactly. So I have this break time, and I consider, as physicists suggest, asymptotic setting when both the diffusion parameter sigma and pulling parameter epsilon go to 0, and I want to find the limit theorems for this tau and the break position. And before, there were a number of work of physicists who used this model as a model of rupture of polymer chains, maybe 24 of works. And there was a couple of mathematical works by Ullmann and Betts, and then Ullmann, Betts, and Martin Heirer, who studied simplest versions of this model, maybe with 3 particles or so, but our results go much further. Okay, now I will explain that actually the problem I consider is actually a large deviation problem for some diffusion in multivariate space. Let us consider the simplest chain where you have only 2 diffusion particles, and totally there are 3 of them, and imagine there is no pooling, epsilon is equal to 0. Then particle 0 is fixed, particle 3 is fixed, and only 1 and 2 are moving. Then actually what you get is the problem of finding exit time and place for a 2-dimensional diffusion. The picture shows the following. Let us consider the following coordinates. The first coordinate is the distance between these 2 particles, and the second coordinate considers this distance. And so you start from the point 1, 1, and then your trajectory is this red line, and the exit time is just an exit from a blue triangle. This line corresponds to and this line correspond to the break here or here, and this diagonal line corresponds to the break in the middle. So just the break position corresponds to the side of the triangle which you reach the first. And this is, of course, while our diffusion coefficient is small, this is just a large deviation event. And so we have to compare the probabilities of 3 large deviation events. However, the standard large deviation principle doesn't help here, because from the point of view of the large deviation theory, what you get is a logarithmic asymptotic, and logarithmic asymptotic is the same for all 3 large deviation events. And to compare them correctly, you need finer probability asymptotic. So it's not that simple as one may believe starting to work with such a problem. Now, I just want to add that if epsilon is positive, then there is a pooling. Then you essentially have the same, but there is one difference, that triangle shrinks in time, so that eventually it vanishes, and this is the deterministic bound of the exit time. Otherwise, it's also an exit problem, but an exit problem for a variable domain. Okay, now I'm going to discuss and to describe the results. Actually, so we have 2 parameters, epsilon and sigma, pooling and diffusion, and both of them go to 0, but the result depends on the interrelation. So we have actually 3 zones. One blue zone at the bottom where the pooling is dominating. The yellow zone is a zone where diffusion is dominating. And there is a most interesting red zone in the middle where both pooling and diffusion are important. And let me describe all 3 zones and the corresponding results. So the first is the blue zone, the dominating pooling, fast pooling regime. It is described by the condition epsilon over sigma goes to infinity. Here, pooling is much faster than the system can react on. The break position is the last link. You just break one particle from the rest, and the break time turns to be almost deterministic. Formally, it means the following. So recall that T star is d over epsilon is a deterministic upper bound for the break time. So the theorem is like this. Let epsilon and sigma go to 0, and epsilon is much bigger than sigma. Then probability that the break position is d goes to 1, while all the rest probabilities go to 0. So we break at the last link. And for the break time, we have the following. We have this critical, not the critical, deterministic bound minus some constant plus something that goes to 0 in probability. So essentially, we break
sorry,
it. Yes.
T star is going to be very large, right? That's the point.
This goes to infinity.
Yeah.
Yeah, this goes to infinity, but this means that we almost wait up to the limit time, up to this constant. This is a constant, and this is 1 over epsilon, much bigger. Okay, this is a deterministic. This is a deterministic. And now I move to the red zone in the picture, which is the most important, most interesting maybe, where both effects are important. Here, the break is influenced both by randomness and pooling. And this is the first surprise. what about the break position? Break position is asymptotically uniform on the interior links between 1 and 2 and so on until d-2, d-1. And at the first and the last links, it is also possible, but with probability 1/2 of the rest. While for the break time, when properly rescaled, we have a Gumbel or double exponential distribution in the limit. So let me state it formally. We have the following theorem. Let epsilon and sigma go to 0. Epsilon is smaller than sigma, much smaller than sigma, but not catastrophically smaller, so that if you take logarithm epsilon, sigma squared still goes to 0. Then you have the limiting theorem for the break place. As I promised, you have the same value for the particles with numbers 1 and d, and this value for in the middle. And you have the following limit theorem for, you have the following limit theorem for the break time. Here you take t star and subtract something that goes to infinity. But of course,
probabilities don't sum to 1. I don't understand.
Sorry?
These probabilities don't sum to 1. Something is missing here.
No, I think there is a misprint. 2 should be here, not here. Or something like this. They should sum to 1. Yeah, that was, I was correcting at the very last moment. There are d numbers. Most of them are 1 over minus d-1, and 2 of them are 1 over. No, this is certainly, there is certainly a misprint. There should be 2 here, and here should not be 2. Yeah, you're right. So here we have this Gumbel law in a limit with some parameters that depend on the dimension. So this is a little bit different limit theorem. I will explain later on how it appears. And finally, the very slow pooling regime, which corresponds to this yellow line, then everything behaves like there were no pooling at all. So the break position distribution is the same, maybe with the same misprint, and the break time turns out to be asymptotically exponentially distributed this time. And formally, you have this, again with the same misprint, I'm sorry. And now with some norming, the exit time is distributed exponentially. E is a standard exponential law. Okay, the proofs are quite long and difficult, but I can easily explain the main ideas of the proofs. The picture of Cézanne will help me a little bit. So imagine you see D players playing a series of sequential independent games. So the players have numbers 1, 2, and so on up to D, and the player numbered I has a probability of winning a game Pi. But the sum of these probabilities is smaller than 1, so that it is quite possible that the game, no one wins a game. So they play several games until someone wins. Then the series is over. It's just first year probability problem to find out what is the probability for each player to win the series. Of course, the answer is pi over s. And the distribution of the series length L, it's also clear what happens. It's a geometric law. Geometric law, because the probability that no one wins n games is 1 minus s to the power n. So we have this. This is the first step. Now, what is the second step? The second step is that we make plays more frequent. Now, let's take a small delta and consider the same problem where probability of the win is changed from pi to delta pi, but the games are played more frequently every delta minutes. Delta is small. Then, of course, the probability of winning for each player does not change. It's still pi over s. But the geometric law for the play length is replaced by exponential. Okay, and the final complication. Now the final complication. If the winning probability of each player depends on the game number. Now delta depends on the game number. Pi is replaced by delta L pi. Delta L is the same for all players. So the proportion of the winning probability remains the same during the game. At every game, the relation between the winning probabilities remain the same. Then, of course, the winning probability for each player still remains pi over s, but the series duration distribution may change from the exponential to something else, for example, to Gumbel law. And this is essentially what happens in our problem. I will now construct some dictionary. So there are games symbolized by the picture and the breaks. And what is the dictionary is the following. So a player corresponds to a link in the chain. This is one player, this is another player, and so on. So we have D players. The win means a break at this position. The game corresponds to some time interval. So the time intervals are placed sequentially, and there is a sequence of time intervals as it would be a sequence of games. So the game winning probability corresponds to a probability of the exit during the time interval. But of course, there is a small difference, not that small actually, between the simplified gaming model. So first, we should exclude that two breaks occur at the same time interval, because for the gamers, only one can win the game. So the probability of two breaks on the same interval should be small. Then the time intervals that we represent as games should be separated by smaller but still long intervals in order to make the games almost independent, because in the game model I represented, the games were independent. So we have to introduce between our games some time intervals that make the behavior of our process almost independent. There is a chance to do it because actually the processes that are behind the scene are linear combinations of Ornstein-Uhlenbeck processes with different parameters. So there is a kind of mixing and we can take advantage of it. And finally, we must be able to compare the winning probability. That means exit probabilities for our processes. And there is a right tool called Petersburg lemma that helps to do it. But as I already told you, exit probabilities are large deviation probabilities. And if you look at the Gaussian large deviation probability, it's just some exponent. But the exponent terms are the same for all probabilities. It's just not enough to compare the probabilities of winning for different games, for different players. So we must have exact asymptotic equivalence, some equivalence, and this is what Petersburg lemma does. And it turns out that the decisive terms are not the exponential terms that are all equal, but the next terms, polynomial ones. Polynomial terms are also equal, but there are some different constants, and this leads to a final result. And by the way, I want to represent one interesting part of the proof that is of independent interest and can be formulated quite independently. I don't know whether this is a new result. I hope so, but this result could be proven maybe 50 years ago or so. But people whom I asked could not indicate the equivalent source. So let us consider a stationary Gaussian process, and let h be some small positive number. So we compare the trajectory of the stationary process y and the linear line ht, red line. And of course, since our process is stationary, then there will be some point where the blue line will definitively go under the red line. The maximal time when yt equals to ht. And I am interested in the behavior of this last passage time, capital T, when h goes to 0. Y is the same process, but h goes to 0. Then, of course, capital T goes to infinity, because you may visit the upper part of the picture for longer and longer times. But for every fixed h, this capital T is finite. And we have the following limit theorem for this T. And we will show under appropriate assumptions on y, we will show that when h goes to 0, then T appropriately normalized has asymptotically Gumbel distribution. So this is a result we obtained with my bachelor student, Nikita Karagodin. So let yt be a real valued centered stationary Gaussian process with covariance rho satisfying two assumptions. One is the behavior at 0 that you see on the screen. This is quite a usual assumption, which plays a big role in this Petersburg-Pickens lemma. And let us assume at infinity, there is some very, very, very mild decay of the covariance, smaller than 1 over logarithm. This is sometimes called Berman condition because Berman introduced it for study of the suprema of the Gaussian processes many, many years ago. So h alpha is a Pickens constant. I will not describe what does it mean. It's just some constant that depends only on alpha. And then for each R, we have this limit theorem. So T of H is the last passage time for the shift parameter H that goes to 0. Then as H goes to 0, we have in the limit double exponential or Gumbel law with quite explicit shift and scaling parameter. So roughly speaking, T of H goes to infinity with a speed H to the power minus 1 square root of 2 log H with some additional term of the second order. Okay, this is more or less all I wanted to tell you about the linear model, which is completely in the Gaussian world. Now I will say some words about our last work, which somehow exits from the Gaussian area. So we may consider a nonlinear system where the main equation behaves like this. So now we have some potential u, say 2 times differentiable, and with some other mild assumptions on it. And now instead of linear condition, we have this kind of condition, which corresponds to another representation of the same idea that the particles don't like to be far apart. And we have this break condition as before, and consider the same problem. Now the solution is not a Gaussian process, but still in the most interesting regime, and what was the red zone in my previous slides, where both pooling and diffusion are important, the system behaves exactly as a linear one, where this constant u is just the second derivative of the potential taken at the breakpoint B. So we get the same result with the Gumbel limit theorem, but with a slightly modified scaling. In my former representation, there was no this constant u, there was just this black term, but this is just a matter of scaling.
You're still letting epsilon and sigma go to 0, right? That's the, I mean, it's the same
all the rest remain the same. All the rest remain the same. There is a slight change of the borders, but I will not dwell on this here. The change is very, very slight. So I just want to say that our passage to general potential comes by using 2 steps. First, starting from this nonlinear system, we move to a time inhomogeneous linear system, so that here you have a linear system, and but it is non-homogeneous. Here, this is some function depending on t, namely this second derivative at u, but taken at the point which corresponds to a typical distance between 2 particles. And then the solution becomes Gaussian, and we may move within Gaussian framework and finally arrive to this time homogeneous linear system with this coefficient u, which is exactly phi at the last point, at the deterministic equivalent of the exit time. So we first approximate our system by some Gaussian system, and then we simplify this Gaussian system to compare it to some solvable thing. So the result, our result about general potential actually is nothing but a reduction to the simple linear case that was described in detail before. So there are, of course, some open problems. For example, one could find out what happens at the zone boundaries. For example, what happens when sigma over epsilon goes to some constant. This we guess what happens, but we didn't do it. And most interesting would be consider other similar system. For example, there are works by Malyshev and his students where they consider very similar chains, but they are governed by the second order equation, which in a sense is more natural for me itself anyway. But the only consolation here is that we were not the first who studied this first order system, and people are interested in that, and the new results are obtained. So thank you very much for your attention. Here, for interested people, there are some references. Our articles will appear in Annals of Applied Probability and in Probability Theory and its Applications. And otherwise, you can find them on the archive. So this is the end of the scientific part of my talk. And I will just add that I am representing a new department in St. Petersburg State University that was created this spring. A department called Mathematics and Computer Sciences. We have very good students. You could see it from the talk of Tatiana, who is our first year master student. And we have opportunities to invite people to come to us and make a series of lectures, mini courses, or just lectures and so on. And so if someone is interested to visiting St. Petersburg and to have a good time with excellent students, you are all welcome. Just contact me and I would advise how to organize it when, of course, when this bad time will be behind us. And still, the World Congress of Mathematicians is scheduled for 22, and I hope some of you will come to St. Petersburg at this occasion. That's all I wanted to say. Thank you very much.
Thank you very much. Are there any questions?
I have a question. Sorry, I don't have the video here. In your last part of the talk, when you move to a general potential, is this some sort of a stochastic homogenization? Or is it that here, in this case, it is more direct? It reminds a bit of Langevin dynamics and similar uses in I've seen in random surfaces or height functions. There's a relationship.
I would say it's rather elementary.
Okay, there's
I don't think we used anything really deep. It's just kind of Taylor formula. You keep the first or two terms of a Taylor formula, and then you prove that the rest does not influence that much of your.
Okay. Thank you.
It's not very deep.
Very good. Thank you.
So what happens if
Can I ask a question?
Well, what happens if you start points on a lattice in R2 I mean, is there a literature on that? Presumably that's a physics literature, right? Instead of points on the line,
yeah,
you know, have points
yeah.
in the plane.
I see your question. So you asked what is going in the multivariate case, right?
Yeah, yeah. Instead of everything being on the line, things being in the plane, for example.
Mm.
It's not clear then what breakage meant.
No, I think that mathematically it's quite meaningful, but then you have to decide what does it mean neighboring particles, right? So, so on the line you see what is neighboring particles. In the if you place your particles on the grid, then there are several ways to define the neighboring particles, but it's possible. But I think the main reason why this was never studied is that people were thinking about this as models of polymer chains or something like this. They wanted to model genuine one-dimensional things. Okay. This is how I see it, but I don't know any work where the movement occurs on the plane or in high dimensional space.
Polymer chains makes a lot of sense. Yeah. Okay.
Can I ask a question? I was wondering if you look at the system when T is very large, then the rightmost particle, of course, is very far to the right. But if I rescale the picture, so the rightmost particle is at position 1, then I get these D random points in the unit interval. Can you say anything about the distribution of those D points as time goes to infinity?
Essentially, okay, there is, I think essentially they are uniformly distributed. I mean, until the break, all the distances increase almost linearly with the same speed. But this is only almost, but the break occurs due to some deviation from this uniform picture. So I would even make a stronger statement answering your question. They are almost staying on the grid with respect to each other, but the only difference is that the distance between the elements of the grid grows with time. This is a typical picture here. So the first approximation is a non-diffusion one, where only imagine sigma equals to 0. Then you will see what happens. There will be some deterministic behavior. There will be some deterministic behavior. There's just not the SDE, but ODE, ordinary, the system of ordinary differential equation. And then you will have this not very interesting picture. But all probabilistic effects occur as large deviations from it.
Thank you.
Can you say a word about the interface between the blue and the red region? What happens when you are really almost strong enough to have a leading particle pulling you, but not yet?
Okay, which bound you mean? Between which regions?
Between red and blue, right? So in blue, the leading particle pulls you. In red, you are more or less uniform.
Yeah.
Is there an intermediate? What happens?
Okay. This was exactly what I meant as an open problem, when epsilon over sigma tends to a constant.
I see.
Then roughly speaking, I know what will happen. That then there will be some intermediate regime when you will have some limiting probabilities to break at each position. They will depend on the constant of this relation between epsilon and sigma, but you will not have explicit formulas. So you will have some intermediate movement from a distribution which is almost uniform that I described with a misprint, and the degenerated distribution where the pooling place is located at the last position. In this intermediate regime between red and blue, you will have some limiting probabilities which correspond to some exit probabilities from some domain, multivariate domain, but you cannot expect to get the explicit formula for these probabilities, neither for the limiting law of the
Can you guess the decay of these probabilities as you go away from the last point towards the first point? So will they decay like a power or like exponential? Suppose we have lots and lots of points.
Okay, so sorry, this you go beyond my talk, because in my talk the number of particles is fixed. There would be quite a lot interesting problem if we let the number of particles go to infinity. Then the question about asymptotics will make sense, right? I don't know any works on this, but this is very reasonable, because then it would be a nice model of some continuous media, right? It will be not a chain, but a good model for some one-dimensional continuous media.
Yeah, strings, say.
Yeah, but the point is that usual strings satisfy second-order equation, right? Yes, but you're right. It's a very, very natural way to think about.
Are there any other questions for Mikhail?
I have one. So if you're pulling in a speed which is still super diffusive but not linear, then will you still have a phase transition, only you will not have the strong pulling, something like this, or?
I think that, okay, we did not explore this case, and it's quite natural. I think there should be, anyway, there should be these three zones, but the boundaries will move, of course.
Okay, interesting, thanks.
Any additional questions? Okay, if not, then let's thank Mikhail Lifshits again for a very nice talk. Thank you.
Thank you very much for your presence.
For everyone, happy end of 2020, and may 2021 be better. And see you all next week.
Bye.
Thank you.